Hello. In the previous video, we've seen the following property of symmetric group. A few of them, I'm going to list them one after another. One of the important results that we proved is the following, that every non-identity element of the symmetric group can be written as a product of disjoint cycles, and this decomposition is unique up to reordering the cycles. At the end of the day, we proved that if I give you two disjoint permutations, then they commute. So disjoint cycles can be written in whatever order we would like. From computational point of view, we have also observed the following equation that we call the linking relation. If I give you two disjoint cycles, then I can permute them, and it's easy to understand the cycle decomposition because that's essentially the cycle decomposition of their product. Now, if I give you two cycles where they have only one element in common, then the linking relation is going to help us to find the cycle decomposition of their product. In fact, their product ends up being a single cycle, a single long cycle. Okay, what single long cycle are we talking about? If I write the numbers in a way that the common point is at the end location of the first cycle and it is at the beginning location, at the starting location of the second cycle, then the product of these cycles is essentially the cycle that you start by writing a sub 1 to the dot a sub m and then continue with the second cycle. Now, here today's topic is about transpositions and product of transpositions. What is a transposition? A two-cycle is called a transposition. So what is a two-cycle? Let's think about it. A two-cycle, let's say A1, A2, just says it's a permutation that flips only two values, 2 points. So if I start writing them like this, so I have 1, 2, 3, and so on. Let's say I'm going to write down the transposition that flips 3 and 4. Then it is like this, then 1 goes to 1, 2 goes to 2, but now I have a kind of cross. 3 goes to 5, and 5 goes to 3, and 4 goes to 4. So I'm flipping two values. That kind of transposition is called, that kind of permutation is called a transposition. Now, the next lemma tells us that every cycle can be written as a product of transpositions. Okay, how can we show this? So I give you a cycle. So we want to say that every cycle can be written as a product of transpositions. If the cycle that I'm given is identity, that doesn't move anything, then of course I can write it as 1, 2 times 1, 2. I'm going to undo what I've done, and that is the identity. So there is nothing to prove when I'm dealing with the identity permutation. So I don't consider identity in the following argument, and then I start talking about two cycles and continue like that. So then again, I'm going to work with m cycles where m is at least 2, because when m is 1, I'm talking about identity permutation, and identity I just discussed how we can write as a product of two transpositions. So we follow by induction on m and prove that an m cycle can be written as a product of transpositions. In fact, that is intuitively what I'm going to do is I'm going to use the linking process again and again and again, and then write down A1, and I'm going to write down A1, A2 times A2, A3. I know that by linking transposition, this is indeed a 3-cycle A1, A2, A3. Now, if I multiply by the next one, A3, I'm going to link that transposition, that 2 cycle with this 3 cycle, and I am going to end up with a 4 cycle. Then the next step, I'm going to get a 5 cycle, and we continue like that till we end up getting an M cycle. So as always, whenever we say we continue like that, that means that there is a hidden induction in the argument. And here I'm going to present the formal argument and use induction to show this. So by induction on M, I'm going to show this equality, that whenever I give you distinct integers, a sub i's, then the cycle a1, a2, a sub m is equal to the product of these transpositions, a1, a2, a2, a3, a3, a4, and so on. When n is 2, there is nothing to prove because the equality just says the transposition a1, a2 is equal to the transposition a1, a2. So the base case is clear. I'm going to show the induction step. What does that mean? That means that I'm going to assume that this equality actually holds for m. Next, I want to show it for m plus 1. That means this is the equality that I want to show the same equality for a1, a2, a sub m plus 1. Okay, but how can I show it? I start with this. I use the linking relation and unlink the last 2, which means I'm going to write this as the product of the first m cycle and then the last 2 cycle. And because of the linking relation, this is in fact correct. If you remember, the linking connection is exactly this, that I can connect an m cycle by another cycle that starts with the same value and have nothing in common. If all the a sub i's are distinct, then I get this equality. I can link them. Now I'm using that equality over here. Now, by the induction hypothesis, I know that the first m cycle can be written as this product. I put them together and I get the desired relation. So I end up getting, so by the induction hypothesis, I know that a1, a2, that this m cycle is equal to the product of these m minus 1 transpositions. And putting this together with the linking relation that we had earlier, we end up getting that the m plus 1 cycle is equal to, instead of this one, I'm going to write down the product of these m minus 1 transpositions and then copy down the last transposition, and we end up getting the desired product of transpositions. So every cycle can be written as a product of transpositions. But we know, because of the cycle decomposition, every permutation, at least every non-identity permutation, can be written as a product of disjoint cycles. Now, every cycle itself can be written as a product of transpositions. So altogether, we get that every permutation can be written as a product of transpositions. So that takes us to the next proposition. Every permutation can be written as a product of transpositions. Okay, so every permutation can be written as a product of transpositions. Let's go through over the argument again, make sure that we all understand it. So suppose that I give you a permutation, sigma. If it is identity, there is nothing to show again. If sigma is identity, I simply write it like this. So I can write it as a product of transpositions. Here I'm assuming that n is at least 2. If n is 1, there is only one element, and that is identity. So there is no transposition, but it's not interesting. So I'm assuming that n is at least 2. So if sigma is identity, we are done. If sigma is not identity, then we prove that we can write this as a product of disjoint cycles. So we show that there are disjoint cycles. Here we don't use the fact that they are disjoint, we just use the existence of such cycles and write down sigma as product of these cycles. Now, every single cycle can be written as a product of transpositions. That is what we showed in the previous lemma. So each sigma I can be written as a product of transpositions. So we write these sigma i's as product of transpositions, plug them in, and we end up getting that sigma can be written as a product of transpositions. And that's exactly what we claimed. Now, unlike the cycle decomposition, this type of multiplication, this type of product is not unique by any means. We can write down a permutation as a product of transpositions in many, many different ways. And it's not, we cannot, I mean, we don't, we can write it, of course, in the trivial way of writing, let's say, identity like this. I can write identity like this, or I can write it like this in a redundant way. And you can say, okay, maybe we can formulate a statement that says two consecutive transpositions should not be the same. But this is not the only issue. We can write down a transposition in different ways. As we can write down a permutation as a product of transpositions in different ways. And the reason that we can do it is not simply because I'm repeating a transposition again and again. In order to show you a non-trivial example of this type, let's recall the fact that how we can conjugate a cycle, and then we'll come back and provide an example for writing a transposition in two different ways. We are going to use this and write down a transposition as a product of other transpositions. Okay, so let's recall, this is an important equation, so I'm taking this chance to recall this equality. We've seen how to conjugate a cycle. So if I want to understand conjugate of the M cycle given by A sub i's, I want to conjugate this M cycle by sigma. That means I want to compute sigma, the M cycle, sigma inverse. We showed that this is indeed a new M cycle. And the new M cycle, support of the new M cycle, is given by sigma applied to the support of the previous cycle. That means, in fact, we show that this M cycle is, we apply sigma to the first entry of the previous M cycle, then the next one, then the next one. And after writing them down, we end up getting the conjugate of A1 under sigma. Okay. Now let's also point out that this one I have already pointed out, but let's point it out in general, that any transposition is its own inverse. If you remember, as I said, a transposition just flips 2 points. Now if I do it again, that means I'm going to flip them back. So that means when I apply a transposition again, when I look at the composite of a transposition by itself, when I look at the square of a transposition, I end up getting the identity map. So every transposition is its own inverse. That's an important rule to remember. So if tau is a transposition, then tau inverse is equal to tau, then tau squared. So if tau is a transposition, then tau squared is identity, and therefore tau inverse is tau. Now I'm going to use these two equations to give you to write down a transposition as a product of other transpositions. So think about the transposition 1, 2. I'm going to conjugate the transposition 1, 3 by the transposition 1, 2. That means I'm going to look at the product of 1, 2, 1, 3, and tau inverse, which is again 1, 2. Now, we know that whenever we conjugate a cycle 1, 3 by a permutation tau, we are going to get another transposition, which is tau 1, tau 3. So I'm applying this tau to the first and to the second elements in this 2 cycle. So we get this 2 cycle, which we call the transposition. And remember, tau of 1 is 2, and 3 is fixed under tau, so tau of 3 is 3. So I end up getting this transposition, which is 2, 3. Altogether, I end up getting this equality. Product of these transpositions, 1, 2, 1, 3, 1, 2, 1, 3, times 1, 2 gives me another transposition, which is 2, 3. So this equation is not clear from the surface, and this shows that I can write down this transposition as a product of transpositions at least in 2 different ways. I can either write it as 2, 3, or I can write it as 1, 2, 1, 3 times 1, 2. In fact, instead of 1, I can put any other number that's different from 2 and 3. So if I was working in S sub 4, if I can put here 4, 2 times 4, 3 times 4, 2. So there are many, many different ways that a transposition can be written as a product of transpositions. Okay, so the amazing thing is, so now that we cannot prove uniqueness, we might give up any hope of understanding this product. But the amazing thing is that even though we can write the transpositions in different ways with different numbers, you see here I have only 1 transposition, here I have 3 transpositions. But nevertheless, there is this amazing fact which says if you end up writing a permutation as a product of transpositions in 2 different ways, let's say you write it as a product of tau sub i's and tau sub i's are transpositions, and you also managed to write it as a product of other transpositions, let's call them sigma sub i's. So both tau sub i's and sigma sub i's are transpositions. Even though you can do it and m and n can be different, as we see over here, that there are 3 of them here and 1 of them in this side. But in whatever method you do, either both m and n are odd or both of them are even. In a compact way, we can say that m should be congruent to n modulo 2. As we can see here, there are 3 here and 1 here, so both of them are odd. That's the amazing fact that we are going to show. That if I write down a permutation as a product of transpositions in 2 different ways, then m should be congruent to n modulo 2. So again, alternatively, it means that either both m and n are odd or both of them are even. We simply say that m and n have the same parity. Okay, so let's formulate this statement, write it down, and try to prove it. So again, what are we claiming? We are saying if tau sub i's and sigma sub i's are transpositions, there are n tau sub i's and m sigma sub i's. If it happens that the product of tau sub i's is equal to the product of sigma sub i's, then m should be congruent to n modulo 2. Okay. First thing that we do is to bring all the sigma sub i's from one side to the other, and that way I get an equality that product of bunch of transpositions is actually the identity map. Then I have to discuss, of course, identity can be written as a product of 0 number of transpositions. So that means that if I manage to write it as a product of bunch of transpositions, that number should be even. And that's our first step. We want to say it's enough to investigate the identity map. It's enough to show that if I manage to write down identity as a product of k number of transpositions, then k should be even. Okay, so I want to say that if we show this statement for identity permutation, then we can deduce the theorem. That's going to be our first step. Okay, so let's see how we do it again. As I've mentioned, I'm going to multiply both sides by inverse of this. Okay, so I'm going to multiply both sides by inverse of this. But remember, inverse of product is product of inverses, but in different order, in the reverse order. So inverse of sigma 1 times sigma 2 dot sigma m is inverse of the last one times inverse of the one before the last one till we reach to the first one. But remember, sigma sub i's are transpositions, and therefore inverse of sigma sub I is itself. So inverse of sigma sub m is sigma sub m. Inverse of sigma sub m minus 1 is sigma sub m minus 1, and so on till we reach to sigma sub 1. So that means when I'm looking at product of transpositions and I want to find its inverse, it's enough to multiply them from the other way, in the reverse way. Okay, so that's inverse of this product. I'm going to multiply that inverse by both sides. So I'm going to multiply both sides of this equality by inverse of this side, and I end up getting that tau sub i's times inverse of this side, and we just computed what the inverse is this guy, should be identity. Okay, now notice that saying m is congruent to n modulo 2 is the same as saying m plus n is congruent to 0 modulo 2. Remember, because I'm working with mod 2 numbers in this case, then negative n and plus n are congruent to each other. That's one way of arguing why these two statements are the same. Alternatively, I can say if m and n, both of them are even, then their sum is even. If m and n, both of them are odd, then their sum is odd. Conversely, if sum of two integers is even, then either both of them are even or both of them are odd. I cannot have an odd number and add it to an even number and end up getting an even number. In either way, you can convince yourself that saying m is congruent to n modulo 2 is equivalent. It happens precisely when their summation is an even number. So in order to show the claim that m is n modulo 2, it's enough to say that the number of terms, the number of transpositions that I have on this side is actually even. So that's exactly what I was claiming. If I manage to show that identity cannot be written as a product of odd number of transpositions, then I can deduce that the number of transpositions that I have over here is even, which completes the argument, because then I get that m plus n is even, and therefore m is congruent to n modulo 2. Okay, so let's see the claim and how we can prove it. So if we show that identity cannot be written as a product of an odd number of transpositions, so identity cannot odd number of transpositions, then we are done. Then we can deduce that the number of transpositions here, which is m plus n, is even, and we get the desired result. So then we focus on the following claim. Suppose I give you gamma i's, gamma 1, gamma 2, gamma k. I tell you that they are transpositions, and we happen to know that their product is actually identity. From here, I want to deduce that 2 divides k, that k is even. We are going to proceed with the following argument. What we will do, we suggest a process. And what does this process do? Under this process, and so this is a type of an algorithm. Under this process, I'm going to look at the elements that appear in the support of these transpositions. I'm going to make sure that the number of elements that appear in the support of these transpositions are getting reduced under this process. So I'm going to eliminate them one after another. That's my goal. I want to introduce a process through which the number of elements in the support of gamma sub i's, either their number disappears or the number of times that they appear in gamma sub i's gets reduced. So I reduce them, the number of appearance of them, I reduce till they get disappear. So when I disappear them one after another, I end up getting no transposition at all. Okay, so now you can say, why is that useful? Because on the other side, we do have identity and there is nothing there. So again, what I will do is to reduce the number of times that these numbers appear in the gamma sub i's, but at the same time, I make sure that at each step, I do not change the parity of the number of transpositions that appear. So if I end up getting 0 transposition at the end, and I do not change the parity of the number of transpositions, that means that the initial number of transpositions should have been even as well, should have been the same as 0. And that would finish the argument. Okay, so let's again think about the process. I'm going to introduce a process through which I'm going to change these transpositions, gamma sub i's. I'm going to change them with the following. So I'm going to change the transpositions, but to still get that their product is identity. So I'm going to introduce new transpositions through which their product will be still identity. The number of appearance of elements in the gamma i's will get reduced, and therefore at some point those numbers will disappear. And so at the terminal point of this process, I get no transpositions at all. But at the same time, I make sure that the parity of the number of transpositions do not change through this process. And so because the final number of transpositions is 0, the initial number of transpositions should have the same parity as 0, and that finishes the proof. So again, let's see the same thing that I have said orally in a written way, and I go over this note. So we are going to introduce a process. In this process, I am going to change the transpositions that are involved, but this change has the following properties. The number of appearance of the largest number in the cycle form of the transpositions decreases. So if I think about these transpositions as cycles, there are 2 numbers appear in these cycles in the support of these transpositions. So in the support of gamma 1, I have 2 numbers. In the support of gamma 2, I have these numbers. I look at the maximum of the numbers that appear in this, and I try to decrease the number of times that this maximum appears in gamma 1, in gamma 2, So I'm going to change gamma i's in a way that the number of times that this maximum thing appears decreases without changing the support, the total support. I mean, I might drop the maximum, but I'm not going to change, I'm not going to increase, I'm not going to add anything to the supports. I'm going to only decrease the number of appearance of the largest number in this transposition products. At the same time, I make sure that the number of transpositions either stays the same, and therefore its parity doesn't change, or it drops by 2, and therefore its parity doesn't change. So in either case, the parity of the number of transpositions do not change. So when I reach to the terminal stage, because each time I'm decreasing the number of appearance of largest number, at some point I should get identity, and therefore that means at some point I should get 0 transpositions. So because of 1 and 2 together, at some point we get no transpositions, which means that the final stage, the final number of transpositions is 0. Now, because the parity of the number of transpositions do not change through this process, the initial number of transpositions should be even as well, and that would finish the proof of the claim. Because the parity of the number of transpositions do not change, the parity of the initial number, which is k, is the same as the parity of the final number of transpositions, which is 0. And that means that k is even. Okay, so I've mentioned a lot about the process, and I promised many things about the process, but let's go into the process. What do I want to do? Again, my goal is to decrease the number of appearance of the largest number. So I take a cycle that is in the largest, where one of the transpositions which has the largest number m, and then I try to move it towards the left in this product. Notice that if the transposition right behind gamma sub I, let's call it gamma sub I minus 1. If gamma sub I minus 1 and gamma sub I are disjoint, I can simply move gamma sub I and toward the left of gamma sub I minus 1, because I can simply commute them because they are disjoint. So I can move this gamma sub I towards the left till I reach to a transposition that's not disjoint from this transposition. Now I have two possibilities. Either the common point of these transpositions, there is only one of them, there is only one common point of the transpositions, their support, and that is M, or there is only one common point and that's not M, or there are two common points and I have to deal with each one of these cases separately. So again, we want to move, okay, here I mentioned all the transpositions that have M in their support toward the left of this multiplication, but you can do it one transposition at a time. So I am going to start with one single transposition, try to move it towards the left. If two transpositions are disjoint, you can simply switch the order of their appearance because they commute. Now, if they are not disjoint, then either they have 2 points in common in their support, and because they are transpositions, there are only 2 points in their support anyway. So if both of them are in common, they are the same transpositions, then I can simply cancel them out. So when I cancel them, what am I doing? I'm decreasing the number of transpositions by 2. And the number of appearance of M also decreases by 2. So both the number of appearance of the maximum decreases and the number of transpositions drops by 2, as we promised. And notice that here I'm not adding anything to the elements that appear in their support. Now, suppose that these two transpositions have only one element in common in their support, and that common element is m. That means I am dealing with the product of a comma m and b comma m, where a and b are different numbers. Okay, so notice that I want to use linking, but in order to use linking, I'm going to write this as m comma b. Notice that they are the same cycles anyway. Now I'm dealing with the product of these two cycles that have m in common, and m is at the end position of the first cycle and the starting position of the second cycle. Therefore, I can use the linking relation and write this as this 3 cycle. Now, what do I want to do? Remember, I want to write this as a product of transpositions where the number of transpositions do not get more than 2. So I want to write it essentially as product of 2 transpositions. But I want to make sure that the number of appearance of m decreases. And here is the magic. I write down this 3 cycle. Notice that this 3 cycle is like this. So it goes from A to M, and then M to B, and from B back to A. But now I can start from M. Instead of starting from A, I can start from M. Then I go from M to B, and then from B to A, and from A I go back to M. So this is the same 3 cycle as before. Now again, I can use the linking relation and unlink these 2 cycles, M comma B and B comma A. Now all of a sudden, product of these 2 transpositions is written as product of these 2 transpositions, and now the number of appearance of M decreased by 1. The elements that appear in the support did not change. Still M, A, and B are the only ones that appear in the support of this and the initial one, but the number of appearance of M decreases by 1. The number of transpositions stays the same. So through this step, the number of appearance of M decreases, even though the number of the number of transpositions did not change at all, and we did not add anything to the support of these transpositions. Now, the third possibility is that these 2 transpositions have one element in common, but that common thing is not M. So it's like this. So they have A in common. A is not B, A is not B, B is not M. So again, I'm going to use the same argument as in the previous case, right? Use the linking relation, put A in the right place in order to be able to use the linking relation, get a 3 cycle, move M. Again, I'm going to move M to the initial point in order to get this 3 cycle, and these 2 are the same 3 cycles, but now the advantage is that when I unlink them, the transposition that has M in it is on the left. So through this process, I can move all the transpositions that have M in them towards the left of this multiplication. But when 2 of these transpositions that have M in them collide, either both of them disappear, and we have an explosion and both of them disappear, or the number of M's gets reduced and we end up getting 1 less M. So we do this kind of moving towards left till we have a collision, and when we have a collision, either both of them disappear or 1 M gets disappeared. So through this disappearing act, we end up getting no transposition at the end, but through this process, the only time that we are removing transposition, we are removing 2 at a time. Then at the end, we get 0 transpositions. The number of transposition, the initial number of transpositions should be even. And the only thing that I have to make sure and say is that what happens if I do these collisions and everything disappears, but then one transposition remains that has M in it. Then how can I get rid of that one? And we have to say that this case does not appear, does not happen. So we use these collisions, we move them towards the left. Whenever I have two of these M's, we get a cancellation. Either we have an explosion and both of them disappear, or the number of M's gets decreased. This process stops when I have at most one M. If there is only one M and this transposition appears at the end of the product, then this process terminates. We want to say that this cannot happen. Okay, so again, this process terminates at some point because I'm reducing the number of M's. At the final state, we cannot have more than one transposition with M in their support, because if we have, then we have either we are colliding these two transpositions, so either the number of M's gets decreased or we have an explosion. So I'm repeating here what I said. So that means that the final stage either has no M, or we are in this kind of format that there is only one transposition that has M in it, and then the other transpositions do not have any M in them. Now let's see what the whole composite does to M. When I feed this composite M, all of these theta i's fix M. Because M does not appear in their support, theta of M is M for every index I. So when I feed the composite M, then first theta sub L is applied to M, I end up getting M back. Then the next one applied to M, I get back M, and I continue like that till we reach to theta sub 2. Then the transposition is applied to M and I end up getting A. So the whole composite sends M to A, but that's not possible because the whole composite is supposed to be the identity map, which is not possible. This means that when I do this process, the terminal state cannot have a single M in it. There is no M. So with this process of moving these transpositions toward left, using the colliding and disappearing, either explosion or disappearing of one of the M's, we get rid of all the transpositions, all the M's that appear in these transpositions. It's not possible to have one M left. And therefore, this process actually terminates with no transposition at all, which completes the proof. Okay, hopefully you understood the highlights of the proof. The highlight of the proof is to produce a process and write down identity as product of new transpositions with the following properties: the number of transpositions, the parity of the number of transpositions do not change, and the number of appearance of the maximum number that appears in the support decreases, and no new number is added to the supports. And therefore, at the end of the final state, no transposition should appear, but because the parity stays the same, the initial parity should have been even as well, and that completes the proof of this theorem. This is one of the important results that we prove about symmetric group and permutations. So hopefully you understood the details of the proof. Now, a permutation, an element of a symmetric group, is called an odd permutation, is called odd or odd permutation if it can be written as a product of odd number of transpositions. And it is called an even permutation if it can be written as a product of even number of transpositions. Now, accordingly, I can define the following sign function. We call it the sign function on the set of unsymmetric group, the set of permutations. Sign of a permutation is either 1 or -1, depending on its parity. Sign of an even permutation is 1, and sign of an odd permutation is -1. Now, we notice that the set 1, -1 under multiplication is a group. So when I multiply 1 by 1, I get 1. 1 times -1, I get -1. And -1 times -1 is 1. So 1 is the identity of this. This is, in fact, a cyclic group of order 2. It's isomorphic to Z sub 2, but we often write it like this in a multiplicative form. Now, a consequence of the way that we defined odd and even permutations is the following important theorem, that the sign function from the symmetric group to the multiplicative group 1, -1 is a group homomorphism. So let's see why this is the case. That means I need to check why sign preserves the group operation. So I give you two permutations, sigma and tau, and I write down sigma as a product of transpositions, sigma sub i's, and I write down tau as a product of transpositions, tau sub i's. So sigma sub i's and tau sub i's are transpositions. Now I notice that by definition, sign of sigma is simply -1 raised to power the number of transpositions that are involved in writing sigma. Again, notice that if n is even, then sign is 1, and that's identical to what we have over here. -1 raised to some even power is 1. And when n is odd, then -1 raised to some odd power is also -1, which is consistent with saying that sign of sigma is -1. So this is a nice way of writing sign of sigma. It's -1 raised to power the number of transpositions that was needed to write down sigma, to get sigma. So similarly, we have that sign of tau is -1 raised to power the number of transpositions needed to write down tau. So we get that sign of tau is -1 raised to power m, sign of sigma is -1 raised to power n. Now when I write down sigma tau, sigma is product of these n number of transpositions. Tau is product of these m number of transpositions. So sigma tau can be written as a product of m plus n many transpositions. And therefore, sign of sigma tau is about parity of this number. So sign of sigma tau is -1 raised to power m plus n. This tells me that this number is 1 when m plus n is even, and this number is -1 when this number is odd. That's exactly what sign of sigma tau is supposed to be. Now, notice that -1 raised to power m plus n is -1 raised to power m times -1 raised to power n. Therefore, using these equalities, we deduce that sigma, sign of sigma tau, is the same as sign of sigma times sign of tau. And this completes proof of this theorem. So sign is a group homomorphism from the symmetric group to the group with two elements, 1 and -1. In particular, kernel of sign is a subgroup of the symmetric group. And kernel of sign, what is it? By definition, it consists of those permutations where the sign goes to the neutral element of the codomain. Neutral element of the codomain is 1. So this means I'm looking for those permutations whose sign is 1. But remember, sign of permutation is 1 precisely when it is an even permutation. So kernel of sign consists of even permutations. I mean, the set of even permutations. The set of even permutations, therefore, is a subgroup of the symmetric group. This subgroup is called the alternating group, and we denote it by A sub n. So the alternating group, A sub n, consists of all even permutations in S sub n. Now let's do some examples. So for instance, when I give you an M cycle, is it odd or even? When is it odd? When is it even? How can I say depending on M? Okay, here is the solution. We have already discussed, in order to understand if it's odd or even, this means that I need to write down sigma as a product of transpositions, and then from there I have to say, do I need odd number of transpositions or even number of transpositions? But we have already discussed how to write down an M cycle as a product of transpositions, essentially using the linking relation. And unlink it, unlink it, unlink it, and so on. So instead of working with this M cycle, I am going to write this as product of M minus 1, 2 cycles using the linking relation, as we did earlier in this video. So I'm not going to go over the argument again, and I simply say that using the linking relation, we can write down this M cycle as a product of M minus 1 transpositions, as we are doing right here. Now, that means this M cycle is odd if M minus 1 is odd. That means M is even. And this M cycle is even if M minus 1 is even, which means M is odd. So the parity of this M cycle is actually the opposite of the parity of M. So an M cycle is even exactly when M is odd, and an M cycle, and therefore an M cycle is odd exactly when M is even. Okay, now let's see another example. The parity of the permutation and its conjugates are the same. So parity of a cycle, and parity of a permutation does not change under conjugation. So I want to say that if sigma is even, then every conjugate of sigma is even. Okay, what does conjugate mean? Let's recall that. A conjugate of sigma is of the form tau sigma tau inverse for some permutation tau. Saying that they have the same parity is the same as saying that they have the same sign. So this is an important technique. We use this sign and use the fact that sign is a group homomorphism to understand parity of permutations. Instead of saying that parity of tau sigma tau inverse is the same as parity of sigma, I'm going to discuss why sign of sigma is equal to sign of tau sigma tau inverse. So I pick a permutation tau and I try to understand sign of this conjugate of sigma. Notice sign is a group homomorphism, therefore sign of product is product of signs. So it is equal to sign of the first times sign of sigma times sign of tau inverse. But remember again, because sign is a group homomorphism, I can pull out this inverse. Sign of tau inverse is the same as sign of tau inverse. Now, notice that this group 1, -1 is an abelian group. I can write down their product of elements in this group in whatever order I wish. Therefore, I can put this guy before sign of sigma and then cancel this out. Because they are abelian, this can cancel out this one. In S sub n, I cannot do it because in S sub n, these do not commute. These do not necessarily commute. So I cannot simply cancel these guys out because I am not allowed to switch the order of tau and sigma. But in this group, I am allowed to switch the order of the terms, and therefore this one cancels out this one. I end up getting sine of sigma. And that's exactly what we wanted to show. We showed that this permutation and this one have the same sign, and therefore sigma and tau sigma tau inverse have the same parity. And that's exactly what we wanted to show. Now let's see another result of this type. So suppose sigma is odd. Now, no matter what tau is, I want to show that tau sigma tau is also odd. So parity doesn't change as I multiply sigma by tau from both sides. So again, similar to the previous example, we are going to use the sine function. It's enough to argue why sine of sigma is the same as sine of tau sigma tau. Let's apply sine to this. Sine of this product is product of sines because sine is a group homomorphism. So it is sine of tau times sine of sigma times sine of tau. But remember, these are elements in this abelian group, so I can put them in whatever order I want. I can put this guy before sine of sigma. I get sine of tau squared times sine of sigma. Now again, notice that every element here squared ends up being 1. 1 squared is of course 1. Negative 1 squared is again 1. So because of this, I know that sigma tau squared is definitely 1. So I can get rid of it. I end up getting sine of sigma. So sine of tau sigma tau is simply sine of sigma. And therefore that means tau sigma tau has the same parity as sigma. Okay, now let's look at the next example. If I give you two permutations, then this tells me how much they do not commute. If they do commute, then this product is 1. If they do not commute, I get some permutation. And claim is that no matter what sigma and tau are, this permutation is an even permutation. It is going to be in the alternating group. So again, I'm going to look at sine of this transposition, sine of this permutation, and try to see, try to show that it is in fact 1. Remember, this is a kernel of sine. This consists of even permutations, which is exactly kernel of the sine function. So I want to show that sine of this transposition, sine of this permutation is 1. Again, use the fact that sine is a group homomorphism and write this as product of sines, sine of sigma times sine of tau. Because sine is a group homomorphism, sine of sigma inverse is the same as sine of sigma inverse. And then this one is sine of tau inverse. Because this is an abelian group, I can reorder these terms. I'm going to put this before sine of tau, and then I get sine of sigma times sine of sigma inverse times sine of tau times sine of tau inverse, and all together I end up getting 1. And that means that this is in the kernel of sigma, which completes the proof. Okay, so this is a rather short video about odd and even permutations and how we can determine whether or not a permutation is odd or even using the sine function. We'll continue in the next video by understanding basic facts about order of elements, and we continue with understanding how to find order of a permutation.